Hello and welcome to G Fun Facts Online. Today we are diving deep into the engineering frontier of astrophysics. We are talking about the unseen machinery that allows us to listen to the universe. Specifically, we are looking at a new technology with a chilly name but a very hot mechanism, FROSTI. It stands for Front Surface Type Irradiator, and it is the key to the next generation of gravitational wave detection. To understand why this technology is so critical, we have to first appreciate the sheer absurdity of what we are trying to do when we listen for gravitational waves. On September 14, 2015, humanity changed. The LIGO Observatory detected the merger of two black holes. It was the first direct detection of ripples in the fabric of spacetime. But to make that detection, the machinery involved had to measure a change in distance smaller than 1,000th the width of a proton. That is not just precise, it is on the very edge of physical possibility. To achieve that, detectors like LIGO, Virgo in Italy, and KAGRA in Japan use massive lasers. They split beams of light, send them down 4-kilometer-long arms, bounce them off mirrors, and recombine them. If the arms stretch or squeeze by even a subatomic fraction, the light shifts and we get a signal. But here is the trap. It is the paradox of power in gravitational wave astronomy. To get a clear signal, you have to fight something called quantum shot noise. Light is not a continuous stream of liquid. It is made of discrete packets called photons. When you are measuring things at this level of precision, the arrival of individual photons creates a flicker, a noise, like rain hitting a tin roof. If the rain is light, you hear every individual drop. If the rain is a torrential downpour, the sound smooths out into a constant hum. To smooth out the quantum noise of light, astronomers need a deluge of photons. They need to crank up the laser power. We are moving from hundreds of kilowatts toward the era of megawatt-scale circulating power in these detectors. This brings us to the central conflict that necessitates FROSTI. When you hit a mirror with a megawatt of laser power, reality pushes back. The mirrors in these detectors are masterpieces of material science, made of ultra-pure fused silica. But even they are not perfect. They absorb a tiny fraction of light, about 1 part in a few million. When you are dealing with a megawatt of energy, even 1 part in a million creates heat. And in the world of precision optics, heat is the enemy. This heat causes two distinct problems. First, there is thermal lensing. As the glass of the mirror warms up, the speed of light traveling through that glass changes due to the thermo-optic effect. The mirror stops acting like a simple reflector and starts acting like a weak lens, blurring the laser beam. Second, and perhaps more physically intuitive, is thermoelastic deformation. The heat causes the mirror to physically expand. The center of the mirror, where the laser hits, bulges outward. Instead of a perfectly flat surface, you now have a bump. This scatters light, ruins the focus, and reduces the sensitivity of the detector. For years, engineers have used heaters to correct this. If the center is hot, they heat the edges to change the curvature back. It is a blunt instrument, like using a sledgehammer to crack a nut. But it worked for the lower power levels of the past. However, as we push for higher sensitivity, a new, more insidious villain has emerged: point absorbers. Point absorbers are microscopic defects. They could be tiny motes of dust or imperfections in the mirror's coating. These spots absorb light much more aggressively than the rest of the mirror. Under high power, these microscopic points get incredibly hot, creating sharp, localized pimples on the mirror's surface. Standard thermal compensation systems cannot fix this. They can correct the overall curve of the mirror, but they cannot smooth out these tiny, specific spikes. These point absorbers scatter light into what we call higher-order modes, complex, jagged patterns of light that the detector cannot use. This is the optical trap. We need high power to reduce shot noise, but high power activates these point absorbers, which ruins the signal. This is where FROSTI enters the stage. Developed by researchers at the University of California, Riverside, FROSTI is an adaptive optics system designed to solve this specific problem. The concept is counterintuitive. If the mirror is distorted because it is getting hot, the solution, according to FROSTI, is to heat it even more. But the key is purely about geometry and homogeneity. A distorted mirror is not necessarily too hot. It is unevenly hot. The laser creates hot peaks. FROSTI projects a calculated heating pattern to target the cool valleys surrounding those peaks. By selectively heating the cooler areas to match the hot spots, it flattens the thermal gradient. It raises the temperature of the entire surface to a uniform state, restoring the mirror's flat profile. Let's get into the hardware, because this is where the engineering shines. FROSTI is located inside the ultra-high vacuum of the detector, hovering near the face of the test mass. It consists of three main components: an emitter array of heating elements, a set of non-imaging optics, and a control system. The non-imaging optics are the secret sauce. These are specialized gold-coated reflectors. Unlike a camera lens that tries to focus an image, these reflectors are designed using complex mathematics to project a specific intensity profile of heat. They sculpt the infrared radiation into a precise shape. Now, you might ask, why go to all this trouble with gold reflectors and heaters? Why not just use a digital projector or a scanning laser to heat the specific spots you need? The answer is noise. This is the most critical constraint in gravitational wave physics. If you use a laser or a projector to heat the mirror, you introduce intensity noise. Lasers flicker. They fluctuate in brightness. If your heating source flickers, the mirror surface fluctuates in response. That physical vibration would look exactly like a gravitational wave signal. You would be blinding yourself with your own flashlight. FROSTI bypasses this by using blackbody radiation from resistive heating elements. Think of the glowing coil in a toaster, but infinitely more precise. Blackbody radiation is inherently stable. A hot piece of metal does not flicker the way a laser does. It has thermal inertia. It provides a smooth, constant stream of photons. This is called low-noise actuation. It allows the engineers to project a heat pattern onto the mirror without adding the jitter that would swamp the detector. This brings us to the operational loop of how this actually works during an observation run. Imagine the detector is running. Sensors called Hartmann wavefront sensors are constantly scanning the surface of the mirrors. They detect a distortion. Maybe there is a general bulge in the center from the main laser, and a sharp spike near the edge caused by a microscopic dust particle, a point absorber. The control computer takes this data and calculates an inverse map. It figures out exactly how much heat needs to be applied to every other part of the mirror to make the surface level again. The system then powers up the FROSTI elements. The resistive heaters glow in the infrared spectrum, invisible to the human eye. The gold reflectors catch this radiation and sculpt it into the required pattern. The mirror absorbs this heat. The glass in the cool zones expands, rising up to meet the level of the hot zones. The pimples and bulges disappear into a flat, uniform plateau. The scattering loss drops, and the detector locks on with crystal clarity. The researchers describe this as ironing out the wrinkles in the space-time sensing fabric. This innovation is not just a patch for current problems. It is a prerequisite for the future. We are currently looking at the LIGO A+ upgrade, which aims to increase the volume of space we can survey by a factor of 7. This upgrade relies on higher power, which means more heat, which means FROSTI is essential. Looking even further ahead, to the third generation of detectors like the Cosmic Explorer in the US and the Einstein telescope in Europe, we're talking about machines that will use massive 440-kilogram mirrors and operate with megawatts of circulating power. These machines aim to see every black hole merger that has occurred in the history of the observable universe. At that scale, thermal patterning is not a luxury. It is a necessity for survival. FROSTI represents a shift in how we build these instruments. We have reached a limit where we can no longer build static, perfect, passive components. The energy loads are simply too high. Instead, we are moving toward active, adaptive instruments. The mirror is no longer just a block of glass. It is a dynamic system that breathes and flexes, controlled by a thermal nervous system that keeps it in peak condition. By using the physics of heat to fight the distortions of heat, FROSTI ensures that our view of the cosmos remains sharp. It allows us to fly close to the sun without melting our wings. As we prepare to listen to the faintest whispers of the early universe, this technology ensures that the static of our own machinery doesn't drown out the story of the stars. That is the genius of FROSTI, and that is how we are sharpening our vision of gravitational waves.